What if everything you think exists in reality is built on an idea so strange that even after decades of thinking about it, your mind still refuses to fully accept it? An idea so simple in form, yet so deep in consequence, that a single sentence from a physicist can stay inside your head for 20 years without ever letting go. That is exactly what happened when John Wheeler once said something that sounded almost like a joke at first, but it wasn't. It was a statement from one of the most influential physicists of the 20th century. Wheeler was not someone you could casually dismiss. He was the man who introduced the term black hole into modern physics. He worked closely with Einstein at Princeton, debating face-to-face with him about the foundations of quantum mechanics. And he also trained Richard Feynman, one of the greatest scientific minds ever known. When a person like that says something unusual, you don't laugh it off. You carry it with you. You think about it. And sometimes it stays with you for decades, refusing to disappear. His idea was this: what if there is only one electron in the entire universe, and it is simply very busy? At first, it sounds meaningless, like a playful thought experiment with no serious value. But the real point is not the sentence itself. The point is why someone like Wheeler would even consider such a possibility. To understand that, you first have to confront something most people accept without question, even though it is far more strange than it appears. Every single electron in the observable universe is absolutely identical. Not similar, not almost the same, not the same within experimental limits. Identical in every measurable way. Same charge, same mass, same spin, same magnetic moment. Every property we can measure gives exactly the same result, no matter where or when we find the electron. It does not matter whether you take an electron from an atom in a laboratory on Earth or from a star in a galaxy billions of light years away. There is no detectable difference whatsoever. None. An electron carries no history. It has no identity tag, no serial number, no aging process. It does not wear out or change over time. In a very real sense, every electron is interchangeable with every other electron that has ever existed. And this raises a deep question. Why? Why should the universe be like this? There is nothing obvious that forces nature to behave this way. You could easily imagine a universe where electrons come in slightly different versions. One that behaves slightly differently after spending time inside a star. Another that changes subtly as it moves through empty space. That kind of universe would still be mathematically consistent. But that is not the universe we live in. In our universe, the identity of electrons is perfect, exact, and unbreakable. And that level of perfection demands an explanation, or at least makes you feel that one is needed. Modern physics gives a very precise answer. In quantum field theory, electrons are not treated as individual little particles moving through space. Instead, they are excitations of a single underlying field that exists everywhere in space and time, the electron field. From this perspective, an electron is not a thing traveling through space. It is a ripple in a field. And every ripple in the same field must follow the same rules, which is why every electron appears identical. This explanation is mathematically powerful. It works. It predicts experiments with extreme accuracy. But it still leaves something unanswered. It tells you how electrons are identical, but not why the field itself has the properties it does. It does not explain why there is exactly one electron field instead of many slightly different ones producing near identical electrons. It describes the mechanism, but not the deeper reason behind the mechanism. And that difference matters more than most people realize. Because the moment you stop asking why at that level, physics stops being about understanding nature and starts becoming about using equations that already work. So we are left with a strange situation. We have perfect identity in nature. We have a theory that describes it extremely well. But somewhere between the two lies a question that still feels unresolved. And it is at this point that Wheeler's idea begins to feel less like a joke and more like a challenge. Because if every electron is truly identical in every possible way, then what does many electrons even mean? And could it be that what we are calling many is actually something deeper, something unified, something that only looks like many from our perspective? That is where the idea begins to shift from standard physics into something far more unusual. And to understand where this leads, we have to go further into how particles, time, and identity are actually connected at the deepest level of physical theory. And that is where everything starts to get strange. If every electron is truly identical in every measurable way, then the obvious question becomes harder to ignore. What does many electrons actually mean at the most fundamental level? Physics tells us that electrons are excitations of a single underlying electron field that fills all of space. In that picture, there are not countless separate little objects flying around. There is one continuous entity, and what we call particles are just localized disturbances in it. That already pushes intuition in a strange direction, but it still keeps the idea of many events happening in different places. Wheeler's suggestion goes further. And this is where things start to feel unsettling in a very precise way. He imagines something even more radical. What if all electrons are not just identical, but in a deeper sense, the same electron? A single entity moving through space and time in such a complicated way that, from our perspective inside time, it appears as if there are countless electrons existing simultaneously. To understand why anyone would even consider this, we have to bring in how physics treats particles in space-time. In quantum theory, particles do not have simple, classical trajectories. They do not follow one clean path from point A to point B like a tiny billiard ball. Instead, their behavior is described by probabilities spread out across many possible paths. When you calculate how an electron moves, you do not assign it a single history. You sum over all possible histories. Every possible route through space-time contributes to what we observe. This idea becomes even more powerful in Feynman's formulation of quantum mechanics. In his picture, particles explore every possible path, including paths that loop, curve, and even move in ways that defy classical intuition. Now imagine taking that idea seriously across the entire history of the universe. An electron is not just moving forward in time in a simple line. It is part of a vast mathematical structure that includes every possible path it could take. And here is where Wheeler's idea begins to take shape. If you follow all of those paths, including those that move forward and backward in time in the mathematical formalism, the distinction between different electrons begins to blur. What looks like many electrons existing at once could be interpreted as one electron appearing in many places along a highly complex space-time trajectory. This is not standard interpretation. It is not something physics textbooks claim as fact, but it is a way of looking at the same mathematics from a very different angle. To see why this idea becomes even more interesting, we need to connect it with something deeper, the relationship between particles and antiparticles. In quantum field theory, every particle has a corresponding antiparticle. For electrons, that partner is the positron. Same mass, opposite charge. When they meet, they annihilate. But mathematically, something surprising happens in Feynman's framework. A positron moving forward in time behaves exactly like an electron moving backward in time. Not as a metaphor, but as a precise mathematical equivalence used in calculations. This means that what we call matter and antimatter are not fundamentally separate objects in the equations. They are two ways of describing the same underlying structure, depending on how time is oriented. And this is where Wheeler's idea becomes more than just philosophical speculation. It begins to touch the actual symmetry structure of physics itself. Because if electrons moving forward in time and positrons moving backward in time are just different descriptions of the same entity, then the distinction between this electron and that electron becomes even less fundamental than it first appeared. The mathematics starts suggesting something uncomfortable. Identity itself might be less about objects and more about perspective. And once you accept that possibility, even temporarily, the idea of a single electron weaving through space-time stops sounding like science fiction and starts sounding like an extreme interpretation of real equations. But there is a problem waiting underneath this idea, and it becomes impossible to ignore once we bring in experimental reality. Because if there were truly one electron moving in this way, it should leave behind a very specific signature in the balance between matter and antimatter in the universe. And that is where the idea begins to face serious tension with what we actually observe. The moment we compare Wheeler's idea with actual observations, a serious problem appears. If a single electron were weaving through space-time in such a way that it repeatedly appears as many electrons, then the same process should also produce its time-reversed counterparts in a balanced way. In the mathematics of quantum field theory, forward-moving electrons and backward-moving equivalents naturally connect to positrons, the antimatter version of electrons. So if Wheeler's picture were literally true in a straightforward sense, we would expect a kind of symmetry, not just electrons everywhere, but a comparable presence of positrons as well. But that is not what the universe shows us. Instead, the observable universe is overwhelmingly made of matter. Electrons are abundant. Positrons exist, but they are extremely rare in comparison. This imbalance between matter and antimatter is one of the biggest unresolved questions in cosmology. Why did the early universe not produce equal amounts of both? Why is there a strong asymmetry today? This is not a small technical detail. It is one of the deep open problems in physics, and it directly challenges the naive version of Wheeler's idea. Richard Feynman, who was closely connected to Wheeler's thinking, quickly noticed this tension. If you interpret the electron as a single entity moving forward and backward in time, then you would naturally expect positrons to appear in comparable quantities. But the universe does not cooperate with that expectation. Wheeler's response, at least initially, was not a full rejection of the idea, but a kind of resistance. He suggested that perhaps the missing positrons are hidden inside more complex structures, like protons. It was not a fully satisfying answer, more like an attempt to keep the idea alive while the difficulty remained unresolved. This is an important pattern in physics. Beautiful ideas often survive long enough to be challenged by inconvenient facts. Sometimes they collapse immediately. Other times, they evolve, absorbing the criticism and emerging in a new form. Feynman himself approached the idea differently. Instead of insisting on a literal interpretation, he focused on what the mathematics was actually doing. In his formulation of quantum electrodynamics, the behavior of electrons and positrons could be treated as different directions along the same mathematical paths. In his famous diagrams, time is not just a background parameter. It becomes part of the bookkeeping system of interactions. A line representing a particle moving backward in time is interpreted as an antiparticle moving forward. This is where the idea becomes more precise and more powerful at the same time. It stops being a philosophical claim about a single electron and becomes a computational framework that produces extremely accurate predictions. Quantum electrodynamics is, in fact, one of the most precisely tested theories in all of science. Its predictions match experiments to an extraordinary number of decimal places. That level of accuracy forces us to take its structure seriously, even if we are unsure about what it means in a deeper ontological sense. And here is where Wheeler's intuition still finds indirect support. Even if the single electron picture is not literally correct, the mathematics does suggest something important. The distinction between particles and antiparticles is not as fundamental as everyday language implies. It is tied to deeper symmetries involving time. Once that idea is on the table, another unsettling implication follows. If the equations of physics are symmetric under time reversal, then the direction of time itself may not be built into the most basic laws of nature. Instead, what we call the flow of time could be an emergent property, arising only when many particles interact in large systems. That changes the meaning of identity itself, because if time is not fundamental, then the idea of an electron as a single object persisting from past to future becomes less clear. What we call the same electron might be better understood as a pattern traced through a deeper structure that does not care about direction. And this brings us closer to the real tension behind Wheeler's idea. Not whether there is one electron, but what it even means for something to be one in a universe where time, identity, and particles are all defined through relationships rather than fixed objects. The next step takes this even further into how identity connects to information itself, and why that connection may be more fundamental than the particles we started with. Once you start questioning whether electrons are truly separate objects or just different appearances of the same underlying structure, a deeper concept begins to emerge. Information, because in physics, identity is not just about what something is, but about what distinguishes it from something else. And distinction is ultimately a question of information. If two electrons are truly identical in every measurable way, then there is literally no information that separates them. No label, no tag, no hidden variable that says this one is here and that one is there. In a strict physical sense, swapping them changes nothing observable. This is not just a philosophical curiosity. It has real consequences in quantum mechanics. When you deal with identical particles like electrons, the rules of quantum theory force their combined states to behave in very specific ways. If you exchange two electrons, the mathematical description of the system does not remain the same. It changes sign. This subtle requirement leads directly to the Pauli exclusion principle. And that principle is not a minor detail. It is one of the foundational reasons why matter has structure at all. It explains why electrons stack into atomic shells instead of collapsing into a single state. It is why atoms have chemistry, why molecules form stable structures, and ultimately why solid matter exists in the form we experience. So, the indistinguishability of electrons is not just an abstract statement. It is built into the stability of the universe. Now the question becomes sharper. If indistinguishability is so fundamental, what does it say about identity itself? In classical physics, identity is straightforward. You can track objects, you can label them, you can say, this particle is the same one that was here earlier, but in quantum physics, that kind of labeling breaks down completely. The universe does not preserve individual object identities in the way classical intuition expects. Instead, what it preserves is structure, symmetry, and information content. This is where Wheeler's idea begins to connect with something much broader than electrons. If identity is not attached to objects but to information patterns, then the question shifts from how many electrons are there to how much distinguishable information is there in the system. And that shift is not just philosophical, it is deeply connected to modern physics, especially in areas like quantum field theory and black hole physics. Because in those domains, information is not just something we use to describe systems. It behaves like a physical quantity. It can be stored, transformed, and in some interpretations, never truly destroyed. This is where the discussion begins to touch one of the most controversial and important problems in theoretical physics: the nature of information in extreme space-time conditions like black holes. The deeper implication is unsettling. If information is fundamental, then particles may not be the primary building blocks of reality. Instead, particles might be secondary expressions of something more abstract, a web of information encoded in fields, space-time, and quantum states. From this perspective, an electron is not a tiny object that exists independently. It is a manifestation of a deeper informational structure that pervades the universe. And if that is true, then Wheeler's provocative question, what if there is only one electron, starts to transform. It may not be a literal claim about a single particle traveling through time. It may instead be pointing towards something more abstract, that what we call many electrons might be repeated expressions of a single underlying informational reality. But even this interpretation leads to another unresolved question. If electrons are expressions of a field, and fields are expressions of mathematical structures, then what exactly is a field? What is the electron field, not as an equation, but as a thing that exists in reality? And that is where physics reaches its current boundary. At this stage, the question stops being about electrons alone and starts becoming something much more fundamental. If electrons are identical because they are excitations of a single field, then the real mystery shifts away from why are electrons the same and moves towards something deeper. What is a field in the first place? Because in quantum field theory, the electron is not treated as an independent object that travels through space like a tiny particle. Instead, it is described as a localized excitation of a continuous entity that exists everywhere. This entity, the electron field, is present throughout the entire universe, even in regions where no electron is detected. That description is mathematically precise. It is one of the most successful frameworks in all of science. But it raises a question that the equations themselves do not fully answer. What is this field? Not what it does, not how it behaves, but what it actually is, in physical reality. When physicists say that an electron is a ripple in a field, they are giving a model that works extremely well for prediction. But the moment you ask what the field is made of, or where it exists in any intuitive sense, the picture becomes less clear. The field is not a substance like water or air. It is not located in space in a simple way, and yet it defines how particles behave everywhere. This is where the discussion enters a long-standing divide in physics. Some physicists take a pragmatic view. If the equations work, that is enough. Others, including many foundational thinkers, insist that a successful theory should not only calculate outcomes, but also describe what reality is actually made of. This disagreement goes back to the earliest days of quantum theory. Niels Bohr argued that physics should focus only on observable outcomes, not on imagining an underlying reality behind them. Albert Einstein, on the other hand, believed that without a description of what is really there, physics is incomplete. That tension has never fully disappeared. It still exists in modern quantum theory, just in more sophisticated forms. And it becomes especially sharp when we return to the idea of identity. Because if electrons are not individually existing objects, but expressions of a field, then the idea of many electrons may itself be a kind of illusion created by how we observe and measure the world. From that perspective, Wheeler's idea gains a different kind of meaning. The claim that there is one electron is not necessarily a literal statement about a particle traveling through space-time. It can also be interpreted as a hint that the concept of individual particles might be emergent rather than fundamental. What we call different electrons may simply be different locations or moments where the same underlying structure expresses itself. But even this interpretation does not resolve the deeper issue. Because if everything reduces to fields, and fields reduce to mathematical structures, then we are still left with the same unresolved question: why do these particular mathematical structures correspond to physical reality at all? At this point, physics reaches a boundary where its language becomes less certain. The equations remain precise, the predictions remain accurate, but the meaning behind them becomes harder to pin down. And this is where the discussion naturally moves towards space-time itself. Because if particles are not fundamental and fields are not fully understood as physical objects, then perhaps even space-time, the stage on which everything appears to happen, is not fundamental either. That possibility changes everything. It suggests that space and time might themselves be emergent properties, arising from something more basic, something that is not spatial or temporal at all. And if that is true, then the idea of a single electron moving through time loses its literal meaning. Instead, what remains is a deeper structure that gives rise to the appearance of motion, identity, and multiplicity. In that framework, Wheeler's intuition becomes less like a claim about particles and more like a pointer toward a missing layer in our understanding of reality. A layer where the distinction between one and many may not exist in the way we assume. And once that possibility is taken seriously, it leads directly into some of the most difficult questions in modern physics. how space-time emerges, how information is encoded in quantum systems, and whether identity itself is something fundamental or something that only appears when we observe the universe from inside it. That is where the final part of the argument begins to converge. If space-time itself is not fundamental, then the way we normally think about objects, things existing in space, persisting through time, may only be an approximation of something deeper. In that case, identity is not a property of objects in space, but a feature that emerges from a more abstract underlying structure. This is where modern physics begins to intersect with some of its most difficult unresolved problems, especially in quantum gravity and black hole physics. Because when you push quantum theory and general relativity to their limits, you repeatedly encounter the same theme. Information does not behave like something that can be casually ignored or destroyed. In classical thinking, objects have identities that persist through time. But in quantum physics, especially in systems involving entanglement, identity becomes relational. What something is cannot always be defined independently of everything else it is connected to. This is an important shift. It means that the universe may not be built from isolated objects with fixed identities, but from relationships, correlations, and patterns of information. In that context, the question of whether all electrons are the same electron begins to lose its literal framing and instead becomes a question about how identity is defined at all in a universe governed by quantum rules. If two electrons cannot be distinguished in any possible way, then the distinction between them is not part of the physical description. It is something added by our way of thinking, not something required by the underlying theory. This idea connects directly to one of the most debated issues in modern theoretical physics, the fate of information in black holes.